Have you ever asked yourself where the heavy elements that make up our world and indeed our bodies come from? It's a fascinating question, really. These heavy elements, the ones beyond helium on the periodic table, play a critical role in shaping the universe and life as we know it. From the iron in our blood to the calcium in our bones, these elements are integral to our existence. But where do they originate? The answer to this question takes us on a journey billions of years back and across the vastness of the universe. The quest to uncover the origins of heavy elements is a story filled with challenges, breakthroughs, and mind-boggling facts. From the early days of astronomical observation to the cutting-edge technology we have today, it's been a journey of constant learning and unlearning. Our understanding of the cosmos has been shaped by numerous theories, some that stood the test of time and others that were swept away by the winds of scientific progress. One such theory was the proposed existence of uranium snowflakes, crystallized radioactive elements hypothesized to trigger Type 1, a supernovae explosions in white dwarfs. This theory suggested that an ultra-rare fission reaction could initiate a chain reaction of nuclear fission, releasing enough energy to cause lighter elements to fuse together, leading to a supernova explosion. But it was the recent findings, born out of the eye of the James Webb Space Telescope, that really set the scientific world abuzz. In the fallout of a massive space explosion known as a gamma-ray burst, scientists discovered key ingredients for life, such as iodine and thorium. This explosion, named GRB 230307A, was brighter than all the stars in the Milky Way combined and lasted longer than most kilonova bursts. It was caused by a collision between two neutron stars, located a staggering 8 million light-years from Earth. These celestial events, the gamma-ray bursts and supernova explosions, have been the celestial crucibles in which heavy elements are forged. And it's not just about the elements we know. The discovery process has also revealed the existence of complex organic molecules called polycyclic aromatic hydrocarbons in an ancient galaxy. This discovery has challenged our understanding of star formation and the evolution of early galaxies. The journey to understand our cosmic origins is not a straight path, but a winding road filled with unexpected turns. Each discovery, each breakthrough, brings us a step closer to understanding our cosmic origins. With every celestial event observed, every molecule analyzed, we peel back another layer of the cosmic onion, bringing us one step closer to answering the ultimate question: where do we come from? But why does the creation of heavy elements matter, you might ask? Well, let's dive into it. The importance of heavy elements stretches far beyond their roles in the cosmos. These elements are vital players in the game of life. They form the building blocks of our world, from the iron in our blood to the calcium in our bones, and even the oxygen we breathe. Yes, these elements that were once cooked up in the heart of a star now make up you and me. Recently, scientists have been making some mind-blowing discoveries. Picture this: a massive explosion in space, a gamma-ray burst, more than 1,000,000 times brighter than all the stars in the Milky Way combined. This cataclysmic event, caused by the collision of two neutron stars, has been found to produce key ingredients for life, such as iodine and thorium. These findings suggest that such cosmic events could play a central role in the creation of these heavy elements, and by extension, life itself. But it's not just about us here on Earth. These discoveries also open up fascinating possibilities about the potential for complex life elsewhere in the universe. After all, if these essential elements can be formed in the aftermath of a distant star collision, who's to say that similar processes aren't happening in other corners of the cosmos? Even more intriguing is the discovery of complex organic molecules in an ancient galaxy that existed a mere 1.5 billion years after the birth of the universe. This suggests that the universe had enough time to create heavy elements and form complex molecules even at that early stage. So when we talk about the creation of heavy elements, we're not just discussing star stuff, we're talking about the stuff of life, the elements that make up our world and possibly others. We're talking about the elements that allow us to exist, to breathe, to think, and to wonder. Without these heavy elements, life as we know it may not exist. Yet, even with these discoveries, many questions remain. The universe in all its infinite complexity is far from being fully understood. We've observed the production of heavy elements in massive star explosions, yet the mechanics behind these long-lived events and their precise role in the emergence of life are still shrouded in mystery. Consider the gamma-ray burst, GRB 230307A, a cosmic spectacle that outshone all the stars in the Milky Way. It was in this aftermath that scientists found iodine and thorium, key ingredients for life. But how exactly do these kilonova events contribute to the creation of life-sustaining elements? What processes are at play that allow for such transformation? These are questions that continue to puzzle and enthrall scientists the world over. And then there's the hypothesis of uranium snowflakes triggering Type 1, a supernovae explosions in white dwarfs. An intriguing proposition, but one that lacks direct evidence. Could these crystallized radioactive elements really be the spark that initiates a chain reaction of nuclear fission, leading to a supernova explosion? Or is there another explanation waiting to be discovered? Let's not forget the mystery of the complex organic molecules, known as polycyclic aromatic hydrocarbons, found in an ancient galaxy, SPT 041847. Their unusual distribution challenges our understanding of early star and galaxy evolution. What could be causing these variations? Could it be the destructive shockwaves from supernova explosions, or perhaps a disconnect between the light from newborn stars and the molecules? The answers to these questions could have profound implications, reshaping our understanding of the universe and our place within it. But to find these answers, we need more research, more observation, and more curiosity. As we continue to explore and understand, we get to rewrite the story of our universe and our place in it. The creation of heavy elements in the universe is not just a story of our past, but also a glimpse into our future. The exploration of this cosmic mystery opens up a universe of possibilities. Picture this. The very elements that constitute life as we know it are born in the heart of celestial explosions. This realization brings us closer to comprehending our cosmic origins and our place in the grand scheme of the universe. From the kilonova events that give birth to elements like iodine and thorium, to the hypothesized uranium snowflakes sparking supernovae in white dwarfs, we're beginning to understand the cosmic alchemy that shapes the universe. This knowledge could potentially transform our perspective on life's existence beyond our blue planet. Unraveling these mysteries is akin to piecing together an intricate cosmic puzzle. Each discovery, be it the presence of complex organic molecules in ancient galaxies, or the unusual distribution of these compounds, adds a piece to our understanding of the universe's evolution. Moreover, these revelations challenge our preconceived notions about star formation and the early evolution of galaxies. They prompt us to rethink our assumptions and to consider new possibilities. Could similar chemistry occur on other planets? Could the universe be teeming with life waiting to be discovered? Intriguingly, our quest doesn't end with these discoveries. They are merely the stepping stones to more profound questions, more intricate puzzles. The universe, in its infinite complexity, always has more to reveal. In the quest to understand the creation of heavy elements, we are not just looking at how the universe was, but at what it could become. The universe, with its celestial explosions and cosmic alchemy, is not just a testament to our past, but a beacon illuminating the path to our future. A future filled with endless possibilities and discoveries. The story of the heavy elements is the story of the universe itself. Throughout this video, we've journeyed through the discovery process that led us to understand how heavy elements like iodine and thorium are forged in the heart of astronomical explosions, such as the gamma-ray bursts. These elements, the building blocks of life as we know it, are born from the fiery collision of neutron stars, events so powerful they outshine all the stars in the Milky Way combined. We've also delved into the profound implications of these findings. These heavy elements, scattered across the cosmos, have the potential to seed life, raising questions about the origins of our existence and the potential for life elsewhere in the universe. Yet, like any good cosmic tale, ours is filled with mystery and unanswered questions. The mechanisms behind these long-lived events, the role of ultra-rare fission reactions, and the formation of complex organic molecules in the early galaxies remain enigmatic, calling for further investigation. These challenges, however, don't diminish the significance of the discoveries. Instead, they point to a universe brimming with possibilities. A universe where tiny atomic bombs might reside within white dwarfs and complex chemistry has been abundant for at least 12 billion years. So as we stand at the precipice of these vast cosmic mysteries, let's remember that every question we answer only leads to more fascinating inquiries, more paths to tread in our quest to comprehend the universe. If you find the universe as fascinating as we do, don't forget to like, comment, and share this video. Let's keep exploring the cosmos together.